So much space, need to see it all.
Nuclear fusion, a process so simple, but even with today's technology, we are not able to harness it.
I'm in space.
Yes, we are in space. This is a star, the birthplace of solar systems and generators of matter.
I'm in space.
This is where fusion happens every second of every day. But what exactly is it? Fusion is the process by which two or more atomic nuclei fuse together to form a heavier nucleus. This action often releases an unparalleled amount of energy. Only the fusion of two nuclei with lower masses than iron release energy. This means that fusion almost always occurs among lighter elements. There are some exceptions, however, like supernovas. Fusion is so difficult that we are not able to significantly replicate it on Earth, even with protium, the very light isotope of hydrogen that undergoes fusion in stars. Military research began with the Manhattan Project in the 1940s, but was not accomplished until 1951, and the first large-scale fusion explosion was carried out in the Ivy Mike hydrogen bomb test in 1952. It takes an incredible amount of energy to force atomic nuclei to fuse together, considering they are both positively charged. However, if the right amount of force and a considerable amount of luck is provided, the nuclei will ignore the electrostatic forces that normally apply, and the nuclear strong force will cause the nuclei to stick together. Because of this, the most common fusion-capable isotopes are deuterium and tritium from hydrogen. Tritium is an incredibly heavy radioactive isotope of hydrogen, with a half-life of around 12 years. This fact means that there is not enough tritium on Earth to support many fusion power plants, about 2.5 to 3 kilograms worldwide. It is artificially produced, however, by bombarding lithium with neutrons. Deuterium is a common form of hydrogen and can be obtained by separating it from water. Fusion is going to look something like this.
We go together like rama-lama-lama, ka-ding-a-ding-ding-dong. Remember forever as shoo-bop, shoo-body-body, yippity-boom-de-boom. Chang, chang, changity, change-a-bop. That's the way it should be. Whoa, yeah!
As some of you may know, that video isn't necessarily accurate. When deuterium and tritium fuse, the result is a helium nucleus and a free neutron. The escaping neutron contains an enormous amount of energy. Because it is so difficult to fuse, there's virtually no chance of a chain reaction, making fusion one of the safest forms of energy available. Another plus is that the product of fusion does not yield any radioactivity, unlike nuclear fission. Nuclear fusion is so efficient that with around 2 liters of water and around 250 grams of rock are enough to provide the energy for a European family for an entire year. A project being undertaken in France by scientists from all over the world called ITER has the daunting goal of developing a sustainable fusion power plant. According to Professor Dr. Ulrich Salm, director at the Institute for Plasma Physics, ITER will have a worthwhile result by 2035. The goal? 500 megawatts from a burn time of at least 8 minutes. The plasma that the scientists are working with reaches temperatures of over 100 million degrees centigrade. Although slightly difficult, fusion can be performed on Earth due to something called the tokamak principle. The tokamak is essentially a large circular chamber shielded by magnetic coils. Invented in the 1960s in Moscow, it remains the most efficient way to produce fusion power. Deuterium and tritium gas are put into the vacuum chamber, which represents the rewinding of the large transformer in the middle of the ring. Many millions of amperes turn the gas to a plasma, burning at around 100 million degrees centigrade. Plasma is the mixture of free electrons and ionized atomic nuclei, which are the perfect ingredients to produce fusion. You may be thinking, wait, if the plasma is 100 million degrees, why doesn't the chamber melt? Well, that is due to the magnetic coils. Because plasma has a mass of free electrons, It can be contained within a magnetic field. Even with the magnetic field, the walls of the chamber will substantially heat up, so they must be made of heat-resistant materials, like graphite and tungsten, which must be tested under nearly every condition imaginable to keep the reactors safe and operational. Although fusion power is many years away, there is no doubt in any physicist's mind that it will be our future. Eventually, the rising costs of fossil fuels will intersect with the plummeting costs of alternative energy. When that happens, mankind will finally be able to support itself in ways so advanced that we can't even imagine what will become of us. The best part about it all, this will happen in our lifetime.
I'm your only friend, I'm not your only friend, but I'm a little glowing friend, but really I'm not actually your friend, but I am. Blue canary in the alley by the light switch, who watches over you? Make a little birdhouse in your soul, not to put too fine a point on it. Say I'm the only bee